So I'm going to switch topics a bit. So you're developing a computational program with user interface and a computational engine. When you get to the larger problems, they can be really big, and sometimes the solvers that you're going to use can't fit in your computer. And then is when you need some other resources. So I'm going to do a short introduction of what high-performance computing systems are, and then also show what we have here at LU, which you can actually take your Python code that you have developed now and run on. So because Python is platform independent, you can run it on a supercomputer as well. So what is supercomputing? So what it means is, this is kind of a quote I have, but it's a term for the fastest computer currently available. They're typically used for number crunching, scientific simulations, fluid dynamics, nuclear energy research, meteorology. So there's a lot of topics that you need this, but a simpler explanation. It's very time dependent. So 30 years or 40 years ago, supercomputer is like your laptop now. So it's a computer that offers much greater capacity than the desktop computers offers at present. Or it has properties that your normal computer can't match. For example, if you have a large problem that needs like terabytes of RAM, it's really hard to get that into a laptop. So a supercomputer usually have that kind of capacity. You can load large models. Or you need to do your parameter study not in a week, but in a single day. Using a supercomputer, you can run all your parameter studies at the same time, so in parallel. So you can get the results now. So that is, for example, weather forecasting is a great example of where you need to get the results really quickly, because otherwise it's too late. So you need to kind of have the compute power to compute the results fast. For example, also you can do more simulations. If you do crash tests for cars, you need to kind of do many simulations, and you need a lot of resources to do these simulations. You can do them many times at the same time. And also you need faster computers to provide ability to make simulations faster. So for example, the weather forecasting is one clear example. And also computers get faster, but the problem is that your local computer will, in a single core, have perhaps more clock frequency than a supercomputer, but the supercomputer typically has like 6,000 processors. So you can scale a lot bigger. So meteorology, I mentioned once, you need to be able to predict the weather in time for it to be useful. And if you want to resolve weather patterns in a high resolutions, you need a lot of compute power. And you can, of course, simulate it, but if it's longer than the actual weather, then it's no use. So there is a lot of supercomputer in the Nordic countries that simulate weather. Crash testing is also very complicated and resource-intensive finite element simulation. And the only way to do it is actually have real large supercomputers to do it. And by using supercomputers, you can skip some of the real crash tests by doing several simulations in the computer instead. Fluid simulation is also something that is very compute intensive. Simulating, for example, combustion, resolving the turbulence behind a train, for example. And these scale pretty well on supercomputing, so you can divide up your problems in multiple parts and run them in parallel. You can also use multiple nodes to use the memory of all the servers at the same time, and that's it. You can also solve larger problems. You can do a lot of in medicine to simulate drugs in different ways. A lot of the COVID vaccines were actually simulated and developed by using supercomputers. Mechanics, of course. So we are studying linear problems here. They're not very simple to solve. But if you add material models to your simulations, nonlinear behavior, all of a sudden structural mechanics problems become much more resource intensive. So here's an example how you make paper pulp by crushing wood. And that is actually a very energy intensive process. And some of these parts here are parts of those simulations. And these material models are complicated to do and requires a lot of compute cycles. Buckling is also another problem that is nonlinear behavior. And you can, on a supercomputer, you can scale up in memory and also divide up the problem on multiple CPUs and processors. Theoretical chemistry, simulating molecules of different kinds, is actually one of the things that at my center is one of the most common problems. That is simulate how you dock different molecules together. And that is done completely in computer, and then it's verified by actual experiments as well. So a bit about high-performance computing history. So we will go back to 64, so it's really long back in time. Then the computers look something like this. So they filled up a compute data center with cooling and power, everything. And we measure supercomputers in something called flops. And that is a floating point operations per second. So in 1964, there was a machine called CDC 600, and it has 9 million floating point operations per second. Today, we are probably even higher than 6. We are at 20 gigaflops per seconds on a normal computer. So that's really a lot of floating point operations. And if you add the GPU to that, we are in the teraflop range on a single laptop. So in 64, we could do, at most, in a single computer, 9 million floating point operations per second. In 69, we were up to 40 megaflops. An interesting thing here, the company Cray is still around. It's part of HP Enterprise. And they build a lot of the supercomputers we have today as well. So it's a old company. In 76, we had a Cray 1 at 160 megaflops. We had one of these in Sweden. It was really protected by the military, basically, because the US didn't trust us. So they put a lot of protection around this, but it was used for the initial developments of the JAWS planes and also some of the Viggens to do some of the calculations for those stress simulations. In 82, we had Cray XMP, that is 235 megaflops. So still, we are not even close to a no modern PC. 1986, we have the IBM. VPF stands for Vector Processing Facility. This was a special computer. It could only do single instruction per clock, but it could work on vectors. So in parallel, you can actually add vectors together in parallel. So that was Vector Processing Facility. And we had one of these in Lund. And it's around when Lunark started as well that we had this computer. That was what my department actually provided, but I wasn't there at the time. 1989, now we're getting close to a smaller laptop or Raspberry Pi. 1989, 2,144 megaflops. Many of these computers came actually, when you bought one of these computers, they actually came with an engineer. So you actually had to pay for an engineer working on this because they were so specialized computers that you actually needed specialized technicians to work with them when they broke down. Some of them were also liquid cooled. So they were dipped into some kind of fluoride liquid to cool them down. Now we are getting into today's performance. So we have Cray T3D at 13.7 gigaflops. But then something happens. It's around 90s or something like that. We don't have these kind of Cray computers. We actually have normal computers again. So ASCII Red was one of the first supercomputers built on commodity hardware. So normal PC servers connected together in a network. And here we get up to 2.38 teraflops. You can see there's a lot of racks, a lot of cooling equipment. In 2002, Japan built one of the largest computers in the world at the time. And you can see this is almost like a football field. It was called the Earth Simulator. It was designed to simulate weather because they had a lot of tornadoes and stuff like that they needed to kind of get a grip of. So they built this computer with 35.6 teraflops. 2004, we had Red Storm. And because this is a US system again, they have this kind of division. So you have three different colors here. You have black, which is secret things, red, which is open, and then you have this white section here. So they can actually divide up the computer in different parts depending on how much need the black projects needed and stuff like that. But you see, these are racks. They are like 2 meters high, and then it's just, so they're quite big. In 2005, we have Blue Gene. It's a special computer with special processors, a lot of them. And now we are getting to like 596 teraflops. You can see there is a wedge-shaped, this thing here is wedge-shaped, and that is actually not just design, it's actually functional. So it actually blows cool air in here, and it's pushed through the racks through there. So cooling is something that we also have problems with and struggle with all the time because these machines take a lot of power. So just getting back to so 2012, we actually get a teraflop machine, but in a lot less racks. So if you compare here, we are 2002, 35.6 teraflops. And here we can get it in 4 racks. So Alaric was one of the first we get into for the teraflop range. And it's built around this kind of cooling rack. So you have 2 racks here with computers and then a cooling rack between that cools the air. So it sucks the air in from behind the computers, cools it down and blows it into the front of the machines here to cool them down. Then we have in 2008, we are in the petaflop range with the Cray XT Jaguar. And you can see here, this is the cooling again. These are all for cooling. So these are actually also, they are in the megawatt range. So they really consume a lot of power. Roadrunner from IBM, 1.7 petaflop. Aurora, we are 240 teraflops. That's one of our machines. We actually have cool LED displays here as well. It's important to have. Stampede in Texas, 19 petaflops. You can see here they're also using cooling racks here, similar to what we have at Lund. And in 2023, we launched our latest system called Cosmos, which is actually 1 petaflop. But we do it in a lot less. So development means that we can actually put the petaflop in a much smaller footprint than many of us, because development of the computers. A little bit about architectures. So when you come to supercomputers, there are a lot of different architectures. So the normal architecture that we talk about the computer is something called von Neumann, that is a single instruction, single data. So the kind of theoretical processor that you have. Then you have what I showed you before, this vector processing facility, is you have single instruction, multiple data. So you can work on vectors and arrays, but still it's a single processor. There is nothing called multiple instruction, single data. But multiple instruction, multiple data. That is the common way of designing supercomputers today. You have multiprocessors where you have unified memory architecture. That means that you have multiple processors. They see the same memory. And it's the same time to access the memory for all processors. We have something called non-uniform memory architecture. It's is where you have a hierarchy. You have fast memory close to processors, you have slower memory a bit further along from the processors. Your laptops and your computers today are some kind of mix between UMA and NUMA architectures. Because you have the multi-core, but you see you have 4 cores in a computer, or 6 or 8 cores. Those are single processors working on a shared memory space. So that's called shared memory. Then you can also have something called multi-computers. It's where you have multiple computers connected in a network, and they communicate by sending messages to each other. So you have one server running here, and I want to divide my work, and I send a message to another computer. Here is my data. I want to process this data, and it waits for the other data, and then you communicate together to create a supercomputer. So it's where they have memory is not shared, but you send messages between them. So it looks something like this. So in a shared memory machine, like your laptop, you have a single memory, and then you have processors connected to this memory. In a message passing architecture, you still have the processors, but each processor or server has their own memory. And if you want to have share the work, you have to kind of send messages to and from the different processors to each other to create this. And most supercomputers today are a mix of, so each of these processors here is a shared memory machine. So every server in a supercomputer has a processor and memory, but has multiple processors as well. So each server connects to another server using the message passing interconnect, but these two are actually a shared memory machine with multiple cores. So for example, on Cosmos, we have 300 servers. Each server has 48 CPUs in it. So this is one server, and it has 48 processors in a shared memory configuration. So you can send a job that runs on 2 servers, so 2 times 48 cores, and they communicate together the data between, but locally they are a shared memory machine. A bit complicated. Then you can also connect them together. The network is really important. So all the servers in Cosmos are connected using something called InfiniBand, which is a really fast network interconnect, 100 to 200 gigabits per second. But the special thing with this network is it can communicate really many small messages very fast, but also high bandwidth. But it's this possibility of communicating with really small messages is important. Then something that you should be aware of when you are using supercomputers is scalability. So if you look at this diagram, this is a speed-up diagram. So the ideal speed-up is that if you have 10 processors, you should have 10 speed-up. And if you have 50 processors, you should have 50 times speed-up. But usually you will never get that, because if you have communication between your processors, there is an overhead. So usually you have a speed-up line that goes under this ideal speed-up. But then there can be problems that look like this. So for example, if you're going for 60 here, you have a 30 times speed-up. That is still good. But if you have something like here on the bottom here, is it useful to go more than 10 processors? So this is a really bad problem, or if you want to run it on a supercomputer, if it doesn't scale, if you add 50 processors and you still have only 5 times speed up, then it's no use adding more processors. Then you should probably look at your algorithms, because that is then you have a bad algorithm, or you need to think about how you communicate or something like that. So this is the ideal is that if you add processors, you should have a similar speed up. Networking is important. As I said before, we have 100 to 200 gigabit bandwidth, so we can send with a speed of gigabits per second between the nodes. But one other thing that's important is this called latency. In a normal network, your Wi-Fi or something, it takes time to initiate communication. Once your communication has initiated, you can send a lot of things over a network. But in supercomputing, you want to be able to send many small messages very fast, and you don't have time to wait for the other side could become ready. So these networks are designed to be able to send many small packages very fast. And here are some examples of gigabit Ethernet. You can have 100 gigabit Ethernet, which is good. It's the same bandwidth as InfiniBand, but there is a longer latency to be able to send messages. So frequent small messages, high bandwidth as InfiniBand, and we have had basically all kind of networks on our clusters here. So a couple of years ago we had 100 megabit Ethernet, we had 1 gigabit Ethernet, and now we have 56 gigabit and higher InfiniBand. Another thing to mention when it comes to supercomputer is the commodity or Linux-based supercomputers. So in '93, I said before that there's something changed. And this is the guy that actually changed everything. Donald Becker and Thomas Sterling. So they kind of thought, but we have Linux today, we have compilers, we have a standard for communicating between computers. Why don't we build a supercomputer in our PCs? So that was actually what he did. So he bought a lot of white box computers, connect them together with a normal standard network, and he managed to actually create quite cheap and fast supercomputers using just PCs. As I said, the classical supercomputer before Linux revolution, they were really expensive. A lot of resources. Only a few sites could actually pay for them. But the PC, when that entered the market, it actually produced a volume market with really relatively high performance per unit. It was a mass market, so each component motherboard was really cheap, so you can actually build a lot of them and connect them together. And also with the GPUs today, they are really fast, the PCs as well. So you can build quite big clusters using the PC architecture. And that is actually what we are seeing today. So our clusters, they are servers, but they are the standard architecture that we have in the PC world. It uses standard technologies. There's nothing special, higher-end processors, but they're still kind of scaled PCs. So the first cluster they built was 16 486 processors. But everything was just going to the standard computer store in the neighborhood. But what made this work was that you had a free operating system like Linux. Didn't cost anything. You could install it on as many computers as you wanted. But another key factor is what we had a free compiler. So you can actually compile your code without any cost as well. And that made it possible to actually also build things for multiple computers with good efficiency. And there was a standard for parallel programming called MPI, or Message Passing Interface, which made it possible to build parallel software in the same way that they did for the large computers, but in a small scale. And today, as I said before, the current clusters are based on exactly the same architecture that was invented at the time. Yeah, so today we use this kind of method. We just take the standard components that are available from the big vendors and connect them together using a fast network. The thing that we can't build today is really large machines which share memory. So most of these nodes here have shared memory internally, but if you want to build a computer of 500 CPUs that are in a single computer, that is hard to do with commodity hardware. You also have a higher error rate on the components because they are not designed the same quality as the supercomputers, dedicated supercomputers. I'm going to skip this top 500 list. So how do you use clusters? So at Lunark we provide, you can log in using a terminal. This is really old. You get a terminal with a command prompt where you can issue commands. But we also provide a desktop login. So you get a remote desktop where you can log in and use the software. And then when you log in, you get to something called a login server where you have all the software and the compilers. There's a shared file system available on both the front end and the nodes. And you upload your files to this machine. Then you have something that is a bit not the same thing as you're on your computer. So when you have decided what you want to do, you have to create a script, like a Python script, that tells the queuing system what you want to do. So in that script, you you give some extra data, such as this program will run for 2 days. I need 16 CPUs. And then you submit this script to the queuing system, and it will kind of see where there are available resources in the cluster and execute the jobs on the cluster at those points. And this is a script. It's in a special language called Bash. So here you have SBatch. Here say I want to run for 10 minutes. I want a job called data process. Then you load your software, and then you run your software here. And this script you submit to the queuing system, and it figures out where to put the data. So you have a queue. So here comes the jobs. You can see on the X scale here, you have the length of the jobs, and the Y scale, you have the number of servers that you need. So the scheduler here, or the queuing system, will try to figure out where it can execute the nodes. So you have the nodes here from 0 to 252, and then it tries to kind of schedule that in an optimal way so everybody gets time. So it's like you book a time in the washing system where you want to wash your clothes, that you kind of need to put a key in somewhere to reserve your time. But the scheduler will make that for you. So it's a really advanced calendar scheduler. Let's see here. I just kind of quickly. So LUNARC is founded by computational chemistry, mechanics, computational physics, and today we have archaeology, humanities, all different areas are requiring high performance computing. And today with AI, it's even more. You need to kind of have big resources to develop these AI models. So it's a lot more research area that's using our computers. And the current one is the Cosmos here, and you can see the back end of our servers. These are servers here, and the network cable in here. The black cables here is the InfiniBand network, and the white ones are the standard network for administration. We have 8 nodes with NVIDIA A100 GPUs. These are for running AI models, for example, graphics applications. A40 is more graphics cards. We also have a cluster for sensitive data analysis, so it's a locked-down version of Cosmos where you have it's more strict on how you can access the internet, for example. This is actually one of our first white box clusters, Linux clusters. It's called Venom64 because there were 64 processors. And it was really built on, the first iteration of this was actually built on IKEA shelves. But we couldn't have them in computer center because they were combustible, so we need to have steel shelves instead. So that's why we have to see here. But it's normal Ethernet cabling, network cabling, just like normal. You have a home connected to a single switch to make them communicate together. Next iteration was Toto 7. That was 128 nodes, 2 to 7. Built on small form factor Dell desktop computers. Looks like this. Took a bit more. You could fit more on a single shelf. This was also after moving down from IKEA shelves, so the cabling is not super nicely done. Sigrid was the first grid computer, which was used for computing, doing computation for the CERN higher in the physics experiments. It was one of our first rack-mounted servers. Lucentan was 210 servers. First 64-bit supercomputer. Also a lot of cabling. More cables. it's really hard to actually get access to those switch cables here because they are really dense. Then we have Milliotto, which was 10,008 servers, and it was an IBM blade system cabling. And here we're also the first time we actually had to think about cooling. So when we actually order a system, our computer center said that you can't start the system because it's too hot. So we had to buy these extra doors which you put on the back, which actually cool them down. So there are cooling elements here. So Siri was the first successor to Sigrid. So this is the grid system, and most of the things here, these big servers here, are actually storage servers. So because they simulated particles moving around, they had to store this to simulate. So the cluster was actually just the bottom part here, and the rest was just storage servers. A blade system from Dell. Plato was 20 teraflops. It's an HP system. And then I showed you already Alaric. And for the next system, we all used the same cooling racks. Just to give you an idea what it actually is to use the computer, I actually have already logged into our desktop on Cosmos. So this is a remote desktop client here I'm using. And we are running Linux, of course, but it's very simple to use. You have all your applications here. So for example, if I want to run ParaView, I can go in here. And then I get asked here, how long do you want to run? So let's see, 30 minutes. And then you also say here, what kind of resource do you want? So I want an, let's say, Intel-based A40 GPU. I can say here I have 4 tasks per node. So that means that I only get access to 4 CPUs on that node, but I get the graphics card. So let's do that. And then I press start here. And now the system asks if there is an available node that I can run on, and it starts the application on that server. So now I'm starting up ParaView, just like I did on my PC here. And let's see here, I can do this one here. So you can see here that I'm running ParaView, and it says on CG13. So this is a server. So now I have requested, so I'm running on a dedicated server, and my ParaView is displaying on my desktop here. And you can see here that I have hardware accelerated graphics available as well. And I can do simulate here the crushing of some kind of tube. So you can see here also how much time I have left. So because this is a limited resource, I can't hog the nodes. So when the time has expired, the application will stop. So if I press stop here, I think I will, yeah, it goes away. But so you can request, and I can also say that I want to run on a node with a lot of memory. So you can specify here, for example, how much memory I want. I want a full node, then I get all the 48 cores of that node to my, and most of our nodes here have 256 gigabytes of memory, so you can actually load quite large models. You can run Colfem. So here I have, we have Visual Studio Code as well, available as well, so you can run the same environment that you have on your own laptop. And now I'm running on a Linux machine here. We will do this one here instead. So you can see here, it's same thing, but now I'm running on a Linux machine. And in a computer center that is like 3 kilometers from here. So in this way you can actually use, you don't have to buy a big machine to have next to your desktop. You just log in, install the client, and you can access the machines here. And you have Visual Studio Code available. You have a lot of different applications. For example, engineering here, we have Abacus. If you are doing a master thesis work on structural mechanics, you will probably be able to use these applications here as well. You can do MATLAB, Python, R, a lot of things here. I can also show you here that we have I can show you how much things are running on node monitor. Slurm. Usage monitor. So this is a tool that shows you how much what is running on the machine here. So you can see here, this is the queuing system here. You can see how many jobs are running here. You can list here, for example, I can sort. So the biggest jobs here are running on 10 nodes using 480 CPUs at the same time. So you can see here that it uses these nodes here, and you can also see how much time they have used. And it consumes a lot of energy. Doesn't look like this here, but these are, I mean, it's 300 servers running all the time, every day. So we consume something like 300 kilowatts momentarily. And that has to be cooled. So just give you an introduction to what supercomputing is. Nothing magical. It's just having a lot of resources that you can use at the same time. So you can do, if you want to do a parameter study, on your local computer you have to wait for each parameter step to finish. With using a supercomputer, you can run every step at the same time. So you can basically get this parameter study run in parallel directly. So, and also we collaborate with structural mechanics. So if you are doing master thesis works, you can get access to these computers as well. There's a lot of them doing that here. And also, if you want to work, of course, developing Colfim, you're welcome to do that as well. So that was what I wanted to show today.